Hey everyone, let's talk about a moment about an axis. And this is kind of an important situation I'm going to show you here with my binder. Let's say I've got the binder, and I'll put this at a little bit of an angle just to make life interesting, and I'm opening it. So here's the binder. The axis of rotation for the cover of the binder is from this left side to this right side, and the left side is higher up, the right side is farther down, and I'll even tilt that towards you. So the axis is at some funky angle. And then I'm going to grab the corner here and I'm going to open up the binder, right? It doesn't matter, I could grab here as well or here, it doesn't really matter where I grab. But the idea here is this is going to rotate about this edge, this axis along the binder edge. Okay, so the idea is I pull up with some force. There's clearly a rotation taking place, right? So there must be a moment. Now, we've done moments around points, and that's going to be just r cross f, but when we do moments about an axis, it's a little bit more complicated, but not too bad. So the idea is I'm going to choose a point on the axis. Could be the left side, could be the right side, could be any place in between. Doesn't matter. It doesn't matter where I choose, but I'm just going to pick a particular point. And then, so let me just choose this lower, actually I'll choose the upper left so you can kind of see things a little bit better. So as I lift this up, and let's say I'm pulling towards me, right? So I'm pulling in the direction of my finger. Okay, so I've lifted this up. There's a force in this direction, right? There's a force this way. And so R is in this direction. So I have an R crossed with an F, right? They're not at 90 degrees. So R crossed with F. So R crossed with F, that's going to create a moment down in this direction. Okay, again, R, cross that with, let's see, fingers in the direction of R, rotate to the direction of the force. So down this way is the moment. So the idea is, if I want to know the moment about the axis, what I want then is the component of the moment along the axis. The component of the moment parallel to the axis. But if we think about this, we've done that before. The component of one vector along or parallel to another vector has its roots in the dot product between those two vectors. So what I'm going to do is I'm going to need a dot product, right? So I need a dot product between the axis, so I'm going to call that AB, and the moment itself. All right, and so I'm going to take the axis and I'm going to take the unit vector along the axis because I don't want any dimensions here. I'm looking for the moment about the axis. So here's my moment right here, and it's got units. I don't want to use another set of units in here. So I'm going to take the component of the moment along the axis. Now that could be along then the unit vector, which is on that axis. And so I need a dot product because that gives me the component of one vector along another vector. Okay, so I need a dot product. So I'm going to need to know what is the unit vector along the axis and then what is the moment. And so doing a problem like this is going to take two things. First off, I need to find the moment. Okay, and again, a moment is generally around one point. Now the moment around A, due to this tension here, and the moment around B are not the same. But I'm going to tell you that when I take the dot product between that, either of those two moments and this axis, I'm going to get the same result. And I'll challenge you, my engineering challenge to you would be to do that. I'm going to take the moment about A. All right, and then we'll find the moment about the axis. But then I challenge you to do the same thing, but take the moment around B, and you should get the same result. All right, so that's the idea then between moments about an axis. So it's going to be a dot product between the unit vector and the actual moment itself. And we're going to see that we can get that using determinants. Remember that the moment, and I'll specify the moment about A, is equal to the determinant I, J, and K, and then R, so this is going to be from A to the line of action of the tension. Again, it doesn't matter if I choose this point or this point up here. It's irrelevant, anywhere along the line of action. So I'm going to take C. So RACX, RACY, RACZ, and then I cross that with the tension. So the tension is going to have an X component, a Y component, and a Z component. So there is the determinant that gives me my moment. And what happens is when I do the dot product here, there's going to be, I'm going to call it RABX unit vector, RABY unit vector. So this is the X component of the unit vector, the Y component of the unit vector, and then RABZ unit vector. And it turns out I can take these components of the unit vector and put them in for the I, J, K. Remember this is going to be a scalar quantity. This is not a vector quantity, it's a scalar quantity. All right, and so if I take the I, J, K's out and I put in the X, Y, and Z components of the unit vector, I get a scalar quantity. And I would need to evaluate that determinant. Okay, so that's one way that we can do that. And let's see what's going to happen. All right, so I'm going to do that in a second video because I know this is going to go long and I'm trying to keep these under 10 minutes and I failed miserably. But all right, so let's stop there and then we'll tackle this more specifically here in just a minute. All right, if you have any questions so far, put them in the comments below.